Alrighty, lads and ladies, welcome back to Calc 1. Nice to see everybody here today. I apologize in advance for my voice sounding a little bit like a lawnmower chewing on a dying rabbit. As I mentioned the other day, my son is sick, and now as a result, my wife and I are both sick. Also, a quick note to Eric. I am trying to leave that book with our unit aide. Our unit aide quit on us Monday morning. She just dipped without any notice. So I don't have anybody to leave that with right now. I've got it right behind me, and next time I'm up on campus, I'm going to keep looking for them. I know they're searching for a replacement, but we might want to find some other way to get that to you. So maybe I could leave it with some library staff or something like that. I'll look into that and see what we can come up with. I'll send you a message. But in the meantime, let's talk about some calculus. So this is MAC2311, section 004, which is Calc 1. And the date today is January 12th, 2022. I remember, this is silly, but every year when I have to get used to writing a new year, I'm reminded of this moment as a late teenager, maybe like 19 years old, sitting on a patio of my first apartment with my buddy. And he goes, "Can you believe it's 2007? Shit, it just sounds like such a big year. It sounds like so much time has gone by. It's crazy." And now here we are writing 2022. It's interesting. It's interesting. So over the last week, we've been talking about limits, right? We've been discussing how to take the limit of a function. I want to do a few things today. One of the things I want to do is revisit some of the problems from that first WebAssign homework. So I realized perhaps a little bit too late that, well, I showed you like one problem where you have to factor and cancel in order to take a limit. There were several problems that required similar but slightly different algebra tricks in order to solve them. So I want to go back and just look at some of those. It seems to me, I looked through the roster and everybody seems to have completed at least most of that assignment, which is quite impressive. But I want to look at a few of these where the algebra tricks are somewhat different and make sure we're all on the same page, because I know when there's a pressure to get an assignment in, sometimes it happens that we care more about getting the answer and typing it in than the procedures necessary to find the limit. So I want to look at, where are we? Is this homework 1 or homework 2? 2. This is homework 1. Some of the stuff from the later part of the limit laws section, right? So some of these towards the end. I trust that like 27 and 28, these sort of things where you're literally just factoring the top and bottom, canceling the shared factor, and then plugging in, those are the same as the problem we did in class together. But number 31, something like this, I would like to look at. I got an email about a problem similar to this number 32. So I think it would be wise to play around with at least 1 or 2 of those to introduce the kind of basic algebra tricks that are very common for problems like this. So I'm going to begin. Let's go back over here. Talking about algebra tricks for limits, which is really reaching back to section 2.3. And then the meat of the conversation today is going to be on continuity, which is the bulk of homework 2. This is section 2.5. And then I would like to talk a little bit, at least get you ready to talk about limits at infinity, limits as x goes to plus or minus infinity. These are different from infinite limits, right? So previously we talked about infinite limits, which are limits where you send x to 2 and then the function is blowing up to infinity there. Here we're talking about limits where you send x to infinity. So whereas the previous infinite limits discussion we had was essentially about vertical asymptotes, right? Finite x values at which the function blows up. Here, we're talking about horizontal asymptotes, right? Using very, very large x values and seeing if the function settles down towards any finite value as we do that. This is section 2.6. Okay. So as promised here, yeah, we are going to look at something like this. We'll go ahead and just do this one. There's some random number generation in here. The red numbers might vary from problem to problem, but the spirit and the technique will be the same. So let me get this guy written down. We'll have the limit as h goes to 0 the square root of 1 plus h minus 1 over h. Let's do it. Nope, that's not it. There we go. Okay. So I don't want to put any particular individual on the spot, but I did see that about 70% of you completed the entire assignment. Can anybody suggest to me a good first step here?
Couldn't you, instead of having it the square root of 1 plus h, you can have it as a like one, what's it called, as an exponent as 1/2?
We can do that. However, that doesn't really help us. So let me explore that reasoning a little bit. It is true that the square root of 1 plus h is the same thing as parentheses 1 plus h to the 1/2. And I think that most of the time when people start exploring this avenue, it's towards this end, right? Hoping to do something like this. So I've written two equal signs here. One of them is true, one of them is not. Which one is the lie? The first equal sign or the second equal sign?
Wouldn't it be the second?
Yes, very good. This is not a true statement. Now it is true that 1 to the 1/2 is 1. So if you could do this, then you could do this. And that would allow you to subtract the 1 away and then work with a much simpler expression. But because this is not true, right? And in general, if you have parentheses a plus b raised to some power, whether that power is an integer, a rational number, an irrational number, positive, negative, whatever, this is pretty much never a to the p plus b to the p. This shit just don't work, right? This is like that. They call it the freshman's dream. Like a plus b squared is a squared plus b squared. It's just not true. You got to FOIL it out, right? And if the power is a positive integer, you can always multiply things out. But if the power is something like 1/2, not an integer, then we're really in trouble. We have no hope of doing anything like that. So you could rewrite this as a power, right? This equality is true. If I wanted to, I could write this as lim h to 0, parentheses 1 plus h to the 1/2 minus 1. But that doesn't get me any closer to being able to get rid of the h downstairs. Really, it's the h downstairs that is a problem for this limit, right? I'm trying to send h to 0. And if I have a factor of h downstairs, that will make this whole ratio undefined when h is 0. So what I'd like to do is find some sort of algebra trick, something kind of similar to factoring the top that will allow me to eventually cancel a factor of h from the bottom. Now, the top is not a polynomial, so factoring ain't gonna happen. We need something else. So if anybody, and I'm looking specifically at the folks who finished the homework set, anybody aware of the trick that will allow me to clean up this numerator?
So I actually, whenever I was doing the homework and I got stuck on this one, I actually pressed the watch it button. So that's the only reason I know it. But do you do the square root of 1 plus h plus 1?
Very good. Yeah, don't be modest. That's good. There's nothing wrong with looking at that video. It's a good thing. That's what it's there for. So there's a special name for this trick. It's called multiplying by the conjugate. Just like complex conjugates, right? Like 1 minus 2i has complex conjugate 1 plus 2i. Any kind of two-piece expression that's separated by a plus or a minus can be talked to as an original and a conjugate. So if I multiply top and bottom by the conjugate of this expression, which is square root 1 plus h plus 1, something nice will happen. Now, if I want to multiply by this upstairs to make my something nice happen, I need to also multiply by it downstairs in order to avoid changing the value of the expression. Holy shit. Don't get sick. Don't do it. It's just not good. So this trick right here is called multiplying by the conjugate. The expression here is referred to as the conjugate of the expression here. And remember, when you multiply fractions, we're always thinking of the tops and bottoms of both as being in parentheses. The reason this works is because of the difference of squares rule. This is like a minus b times a plus b. And we know that that is the factored form of a difference of squares. If you multiply out the top let's do it downstairs. I'll just write that first because we don't have to think too hard about that. Downstairs, I just have h times parentheses square root 1 plus h plus 1. All right, just multiplying the fraction straight across. There's no need to distribute, just leave it like this. Upstairs, we will FOIL. So I have the square root of 1 plus h times the square root of 1 plus h. I'm going to be like ridiculous about this and write everything out. So that's the square root of 1 plus h squared, right? That thing times itself. That's my firsts. My outers are the square root of 1 plus h times 1. So that's just plus the square root of 1 plus h. My inners are minus 1 times the square root of 1 plus h. So that's minus square root 1 plus h. And then my lasts are minus 1 times plus 1, which is minus 1. The nice thing about this trick is that the cross terms, the two terms in the middle, the O and the I in FOIL, are identical but of opposite sign. So these two terms in the middle, they add up to 0, they go away. The other niceness here is that the square root of 1 plus h all squared is just 1 plus h. Right, this piece is just. So my numerator after foiling out is just 1 plus h minus 1. So altogether I have limit h to 0, 1 plus h minus 1 divided by that denominator, h times parentheses square root 1 plus h plus 1. The exponent is going back a little bit. The exponent would not cancel out the square root. The exponent, maybe I want to make sure I'm understanding correctly. This exponent here, if this is what we're asking about, and I apologize for not seeing the chat as it came in, this square will cancel this square root. That is true. If we're talking about back here, does this exponent cancel this square root? No, this exponent is just another way to write that square root. But in this line, the square here does annihilate the square root here, and that's why we get a 1 plus h here. And similarly, Marvin, I'm sorry I didn't see your answer earlier. That's exactly correct. That's all we want to do. All right, so upstairs I've got 1 plus h minus 1. That's just h. And as you solve these problems, please imitate the notation that I'm using, right? Make sure you write your equal signs. Make sure you write your limits. Don't be sloppy about this stuff. I will take off points for incorrect notation on the exam. So upstairs I have h, downstairs I have h times parentheses square root 1 plus h plus 1. And now the top and bottom both have a factor of h. Of course, that top is really secretly h times 1. So when I cancel those, the 1 will survive upstairs, and the parenthetical statement will survive downstairs. So I have left over here limit h to 0, 1 over the square root of 1 plus h plus 1. And the goal this whole time has been to get rid of this h downstairs, right? That's the factor that was causing us so much trouble, because that's the factor that made the ratio undefined when you plug in 0 for h. So now that we've gotten rid of him, we can evaluate this limit just by plugging in 0 for h. When we do that, I get 1 over the square root of 1 plus 0 plus 1, which is 1 over the square root of 1 plus 1. The square root of 1 is 1, so this is 1 over 1 plus 1, or 1/2. All right, so this trick is called multiplying by the conjugate, and it is very useful. Anytime you have a difference of two terms, one of them being in a square root or raised to a weird non-integer power, some flavor of multiplying by the conjugate is worth at least considering. I won't write it. Multiply by the conjugate. That's what it's called. Okay, any questions on any of these steps? Kind of how we knew to do this, or how we chose the thing to multiply by, where this numerator came from, why it simplified to this, any of that?
Can you just kind of repeat the first part about figuring out the conjugate?
Sure. So what we did here is we in general, the conjugate of A minus B is A plus B. So if you have a binomial, right, just two terms, an expression with two terms separated by addition or subtraction, you get the conjugate by flipping the sign in between them. So here we had the square root of 1 plus h minus 1. This is like my A and this is like my B. So this has conjugate square root of 1 plus h plus 1, which is and the term comes from complex numbers, right? Where like 1 minus I has complex conjugate 1 plus I, but it can be generalized to other expressions like this.
Perfect. Thank you.
Yeah, of course. And then the sticking point, of course, if you're going to multiply by this upstairs, you must also multiply by it downstairs. I think there were like one or two others that I wanted to take a peek at. Other questions on this before we move away? Okay. Yeah, 32, I got a question about this. So the reason you're seeing this kind of weird notation, by the way, like limit h to 0, and then something plus h and minus the something without the h. The limits of this form show up in section 3.1 as we calculate derivatives, or actually section 2.8, 2.9, so somewhere around there. When we first introduced the derivative, you'll see a lot of limits like this. So again, we just want to calculate the limit, lim h to 0. 3 plus h to the negative first power minus 3 to the negative first power all over h. The trick here is not to multiply by the conjugate. The trick here is just to write these guys as fractions and have a common denominator. So this numerator looks weird, right? Whereas you cannot do anything really with the square root. You can write it as a power, but then there's nothing you can really do with that power besides look at it. Here, this power can be rewritten in a meaningful way. The rule, of course, that some shit to the negative first power is the same as the reciprocal of that shit. So I can rewrite this expression as a big kind of what we call compound fraction, fractions within fractions. Of course, being disciplined to always write the equal sign and the limit. I know it gets boring, calluses, and this is math life, right? Just get used to it. We're going to be writing a lot. Okay, big fraction, h downstairs. 3 plus h to the negative first, according to this rule, is 1 over 3 plus h. And similarly, 3 to the negative first is 1/3. And while this might look like a step in the wrong direction, it's actually a step in the right direction because we can subtract fractions like these. We can have a common denominator between these two. And in doing so, we will get something nicer. So if I multiply the first fraction by 3 over 3, and I multiply the second fraction by 3 plus h over 3 plus h, I'll get 3 over 3 times 3 plus h minus 3 plus h over 3 times 3 plus h. All of this is still being divided by h itself. So that first and all important step here is having a common denominator. Now that those two little fractions upstairs have been rewritten with the same denominator, I can perform the subtraction. Remembering again that tops and bottoms of fractions are always in parentheses. This is 3 minus parentheses 3 plus h over the denominator. 3 times 3 plus h. And all still divided by h. At this stage, I think it is wise to put the top in a set of big parentheses, because division is not associative, ladies and gentlemen. 1 divided by 2 divided by 3 is meaningless unless you tell me which one's the big fraction. Some things to consider doing in the next stage. Of course, equals lim h to 0 is still there. Of course, we're going to distribute this negative. So this is 3 minus h. The downstairs in this first fraction is still 3 times parentheses 3 plus h. The other thing I would do, I've got this, which was my top. If I want to divide all that stuff by h, rather than writing more messy compound fractions, I'm just going to say this is the same as multiplying by 1 over h. Now 3 minus 3 is 0. So this is lim h to 0. Negative h over 3 times 3 plus h times 1 over h. And the h's cancel. And this gives me lim h to 0. Negative 1 over 3 times 3 plus h. And again, now that the factor of h from the downstairs is gone, I am free to send h to 0. And in doing so, I get negative 1 over 3 times 3 plus 0, which is negative 1/9. Okay. Any questions on any of these steps, kind of the motivation or the execution?
I'm kind of rusty, but why are you multiplying it by 1 over h instead of h over 1?
Fair question. This is something I encounter a lot. So let's take a little detour through algebra land here. Division is a weird operation. What I mean by weird is non-associative. Also, of course, not commutative. Right, so like 3 times 5 is the same as 5 times 3. That's what it means to say that multiplication is commutative. The order can be swapped. 1 divided by 2 is not the same as 2 divided by 1, right? So division is not commutative. The issue that we're dealing with here that is even more sinister is that division is not associative. So what I mean by that is if you write A divided by B divided by C like this, totally ambiguous, has no meaning. So associativity, commutativity means you can swap the order without consequence. Associativity means you can swap parentheses with no consequence. If you have A divided by B in parentheses, and then you divide that by C, this does have a clear meaning. This is the same as A divided by B. And then what you have to do is think of both the top and bottom of the big fraction as little fractions. C is C divided by 1. And that's the role that H is playing here, right? This is like A divided by B, and then all of that divided by C. And then we all know that to divide a fraction, you flip and multiply. The trick is identifying what's the big top and what's the big bottom. Once you have these parentheses, you can say, oh, this is the top and this is the bottom. So if I can think of the bottom as also being a fraction by writing C as C over 1, then when I flip and multiply, I get A over B left alone times this guy flipped over, which is 1 over C. And that's exactly what we've done going from here to here. Now, real quick, if we had the other way around, if I had A divided by B divided by C with parentheses down here, how would I handle that?
Wouldn't it just be A over 1 divided by B divided by C?
Very good. So again, we kind of identify which fraction is the big fraction using the parentheses. So this is the little one and this is the big one. So I treat A as A over 1, and then I'm dividing A over 1 by B over C. So this would be A over 1, and then we flip and multiply the downstairs, C over B. And then I don't even know that, right? You know how to multiply fractions, just multiply straight across. So here, this line is akin to this line. Here's A, here's B, here's C. It's good. I'm glad we're getting this. Oh, it's good stuff. Other questions or comments? By the way, it makes you feel better. Honest truth. I don't know if I told you this, guys. I failed Algebra 1 3 times, right? 8th grade, 9th grade, 10th grade, dropped out of high school in 10th grade, said, fuck math. Came back to college, didn't really understand this stuff about fractions until Calc 1. So you're in good company, right? It's not a shameful thing. This is the truth. If you were to take 10 adults off the street and ask them, what is this? Or even what is this? 9 of them would get it wrong. And 1 of them would still most likely get it wrong out. Okay. Let's take a look at one more of these limit problems, something that's perhaps a little trickier. I guess they don't really get much trickier. The rest of these, yeah, the rest of these all follow the same sort of stuff, right? So if you've got fractions or a power that could be interpreted as a fraction, write it as a fraction, have a common denominator. If you've got a ratio of polynomials, try to factor the top and bottom and get rid of the factor that's causing you trouble. Of course, the very first thing you should try to do with all of these is just plug in the limit, right? If the bottom isn't 0, if you don't end up with an indeterminate or undefined expression, then you're Gucci. So looking through the rest of these, I don't see anything that requires a trick we haven't yet discussed. This guy would be another multiply by the conjugate thing. You could also force factor the top. And the rest of this is just algebra review. So, all right, we'll let the rest of this slide, which means we're ready to talk about continuity. Oh, by the way, if you need more time on that homework set, just submit an extension request in WebAssign. A few people did that already, but if you either did not get to complete it, or you feel like you didn't get to spend the time with those problems that you need to really master them and understand them deeply, please submit an extension request. I'm happy to grant it. I want you to have time working on that stuff. I want you to feel like you are 100% in control of those problems, because there will be problems of that nature on the first test.
Can we still practice those problems even after the deadline?
That's a good question. So from the student perspective, I'm not sure if WebAssign lets you in to review them after the case. Can anybody answer that for me?
It does for some of them. Sometimes it doesn't.
Okay, that's what I was afraid of. So I would just say, if you want to practice some more, just put in an extension request, right? I'll grant it. I'm never going to be like, why do you want this? I'll just grant it. That way you can see everything. So you may notice that we're jumping over section 2.4. Section 2.4 is on the precise definition of a limit, the delta epsilon definition of a limit, which is good stuff if you're into it. As an analyst, I live and die by letting epsilon be greater than 0. But it's a little bit more detailed than you need for this class. So if you want to learn that stuff, there's a class called Advanced Calculus that you can take at university, or like an introduction to real analysis, something like that. You'll get to fiddle plenty with deltas and epsilons. But for us in this class, we really don't need that. At no point will those delta epsilon arguments or proofs be required for any of the stuff we're trying to do. And in general, someone who's trying to use calculus at the level of like an engineer, you really don't need it. But it is worth taking a look at if you're curious about exactly what's going on underneath all of this limit stuff. So when you factor in, canceling, plug in, why does that work? All the details are hiding in these inequalities involving the Greek letters delta and epsilon. But something I do need you guys to understand on a deep level is continuity. So this is the next section we move to. Intuitively, we have an idea of what it means to say a graph is continuous, right? Intuitively, one says that f is continuous if the graph y equals f of x is a single connected piece, i.e., or that is, can be drawn without lifting your pencil. And this intuitive definition turns out to be 100% correct. I can prove that this is equivalent to the definition that we're going to use. But it's not a definition that you can work with very much, right? If I ask you, is this function continuous at 3? You don't want to be like, well, I can draw the graph without lifting my pencil. So yes, right? Because that relies on this very subjective thing of like, how good are you at drawing graphs, and how good is your picture, and how fine is your pencil, and all that. So what we need is a definition of continuity that we can work with mechanically and algebraically. I mentioned kind of in passing the other day that the kind of next level up in rigor, this is the calc definition of continuity. First things first, continuity is something that happens one point at a time, right? We're used to referring to continuity as a global property. This function is continuous, means its graph is always like one piece everywhere, connected everywhere. Really, continuity is something you need to check one element in the domain at a time. So is this function continuous at 0? Is this function continuous at pi? So on. In other words, it's called pointwise continuity. We say f is continuous at x equals a, which must be in the domain, provided the limit as x approaches A of f of x is equal to f of A. This is a slightly more workable definition of continuity. And if you think about it, this requires three things, two of which I have not explicitly mentioned. The first one I'm going to list here is one I mentioned explicitly. F of A needs to exist, right? A needs to be in the domain of the function f. If your function is undefined at 2, there is no way for it to be continuous at 2. All right, the next two things have to do with the limit here. Similar, right? If I have an equality between two objects, I need both of those objects to exist. So I need the limit as x approaches A of f of x to exist. And then even if both of those things are true, it's possible for this definition to fail if this equality is not true. So finally, the limit must equal the function value. I see your chat comment there, Natalie. I'm sorry about that. Between my son, wife, and myself being sick, I am a little bit behind on those. I will clear them out this afternoon. I'm sorry you've had to wait. So continuity, right? We say the function f is continuous at the number x equals a, provided the limit as x goes to a of f of x is equal to f of a, which means the limit of the function is equal to the value of the function. This is the point on the graph, right? This is the y value of the point on the graph. And this is saying the behavior of the graph near that point tends to that point, right? So you can think of this as a local statement. It's a statement about how the graph looks near A. We're saying at A, the function does what the limit suggests it ought to do. That's what it means to say that the function is continuous. These are the three mechanisms that can fail, right? These are the three ways you can break that definition. And each one is sort of associated with some different types of continuities. So I'm going to show you how to classify discontinuities according to which one of these things fails. Quick note, the classic way for number 2 to fail is for the limit as x approaches a from the left of f of x to not be equal to the limit as x approaches a from the right of f of x. Right, most of the time when a limit fails to exist, that's why. There's also that oscillation thing we talked about in the video lecture from Monday. That is another possibility. So let's begin with some pictures. All right. This function is not continuous at A. In fact, oh, I'm so sorry. Pretend this is open. So sorry, can't have both of those filled in. So here, the limit x approaches A of f of x does not exist because the left limit as x approaches A from the left here would be 1, but the right limit as x approaches A from the right of f of x is equal to 3. So if the left limit and right limit are not the same, then there's no chance to be continuous. And we call this a jump discontinuity. Right, because the graph does a sudden boop jump. So this is failing condition 2. Another possibility is where the limits are the same from the both sides. So here the limit does exist, but what's going on here is that the limit as x approaches A of f of x is not equal to f of A. The limit as x approaches A of f of x does exist as you get closer and closer to A from the left or from the right. Those y values are getting closer and closer to 1. So here that limit does exist, it's 1. But the function value there is 2. We call this a removable discontinuity. And these are, in a sense, our favorite discontinuities, as the name suggests, because they can be fixed. If I just force this guy back in here, if I can remove the discontinuity. I could fix this by redefining the value of f of A to be 1. Hence the term removable. I'll put that in parentheses here. Could be fixed by redefining f of A to be 1. That's what we call them, removable.
I have a quick question.
Mhm.
Even if it is removable, but wouldn't it still not be continuous because the limit wouldn't equal the function value?
Well, that's it, right? Yeah. So this is a discontinuity, right? This picture right here describes what's called a removable discontinuity. I could make it continuous by making this come down here, right? If I pick up this point and drag it down here, boop, all of a sudden the function is continuous. But as drawn, yes, this is discontinuous because, like you said, the function value 2 is not equal to the limit value 1.
Thank you.
Sure. There's another flavor of removable discontinuity. And that comes from the violation of the first element. This is almost silly, but just having a hole. I would also call this a removable discontinuity. Here, F is discontinuous at X equals A because F of A doesn't exist. It's not that the limit does not exist here. The limit is fine. The limit as X approaches A from either side is 1, but there's no filled in point anywhere above or below A. In other words here, A is just not in the domain. And again, I could fix this by just defining F of A to be 1. So this is also removable. This is called a hole. And it is also technically removable by defining, in this case, F of A to be 1. All right, so these are the gentler flavors of discontinuity. There are some less gentle flavors. All right. Here we've got real problems, right? First off here, F of A does not exist again. Right, there is no point on the graph whose X value is A. But more severely, the limit as X approaches A of F of X is infinity. We call this infinite discontinuity. And if either of the one-sided limits is infinity or negative infinity, right, it doesn't need to be like this where both sides point up, then we would still call that an infinite discontinuity. So if I give you something like this, still an infinite discontinuity. Even if I fill a point in here like this. infinite discontinuity is a little harder to deal with than any of the removable or even jump discontinuities. Because there's no like tweaking, you know, I could, even with the jump, I could like shift one of those branches up or down to make them meet if I wanted to. But here, there's no like dragging this up till it meets the other part of the graph. These are harder to fix.
We need to know the names of
Yes, you do.
discontinued or discontinued.
Yeah, I know there's, we don't think of vocabulary as being a big thing in mathematics, but here it is the case that you need to learn these names because I may ask you to classify discontinuities by type. In fact, we're going to go a little bit deeper. The blue graph on the left, there is a more nitpicky way to describe this. And in past semesters, I omitted this stuff, but it's hard to give you good questions to play with unless I do. So while I don't want to overwhelm you with terminology, the function on the left down here, this guy, we would say he is right continuous at A. So let me get a bit more granular with the definitions and we'll look at some more examples. So to clearly define infinite discontinuity, here's the rule. If either or both of the limit as x approaches a from the left of f of x, or limit as x approaches a from the right of f of x are plus or minus infinity, then f has an infinite discontinuity at x equals a. I don't want to call this a definition because we're like already within a definition. You can call it a sub-definition or just a rule, whatever you want to call it. If the function blows up at a from either direction, then you're looking at an infinite discontinuity. So even stuff like this, where it's behaving nicely on the right side of that asymptote and it's misbehaving on the left, infinite discontinuity. When I said I'm going to get a little bit more granular with this, what I mean is I'm going to define this notion of one-sided continuity. It's something that matters a little bit to functional analysts. So if you intend to study like quantum mechanics or control systems, this stuff will have some meaning to you. And also it's a good source of questions just to see how well you're understanding the material. Before I move away from this, are there any questions on the definition of continuous or the ways in which a function can fail to be continuous? Okay. And we're going to discuss now one-sided continuity. This is what it sounds like. You just take the definition of continuous and replace that limit by a one-sided limit. So we say f is continuous from the left, or just left continuous, at x equals a, provided the limit as x approaches a from the left of f of x is equal to f of a. And we say continuous from the right, or right continuous at x equals a, provided the limit as x goes to a from the right of f of x is equal to f of a. So these both still require that a be in the domain of f. And what we're just saying is that if you relax the original definition to look just one side at a time, then on whatever side the definition is satisfied, we would say it's left or right continuous. So the examples here, I'm just going to draw one graph. Right. So at a, this function, so what we're going to do is just describe the continuity of f at x equals a, x equals b, x equals c. If we look at x equals a, since this point is filled in, f of a is indeed equal to the limit as x approaches a from the right. Now there ain't jack shit over here, right? The function isn't even defined to the left of a. So here we would say since the limit as x approaches a from the right of f of x is actually equal to f of a, we'd say that f, the function f, is right continuous at x equals a. I can't talk about the overall limit as x approaches a because there's no way to even look at what's coming in from the left. There's no part of the graph over here. But I can look at what happens as I come in from the right. And as I come in from the right, the function's values are tending towards the actual function value there. So we call that right continuous. At x equals b, as I walk in from the left, the limit, so since lim x to b from the left of f of x, which is the limit as x approaches b from the left, that would be this y value, because that's what I'm getting closer and closer to, is actually equal to f of b, the y value of the filled in point there, the function f is left continuous at x equals b. And we can say more here. The function is left continuous. Is it also right continuous at x equals b? the limit as x approaches b from the right, is that the same as the limit as x approaches b from the left?
No,
No, definitely not, right? As x approaches b from the right, we're going up to this y value, which is clearly not this y value. So I would go on here, I would say, however, since the limit as x approaches b from the right of f of x is different than the limit as x approaches b from the left of f of x, f and this is different from f of b itself, f is not right continuous at x equals b. In fact, you might be starting to smell a theorem here, right? What if you had to describe the behavior here in general, you would say this is a jump discontinuity, yeah? So we're left continuous, but we're not right continuous. And we're not continuous overall, right? The Big Daddy continuity definition is not satisfied here either. So the kind of thing that's lying in the background is you are continuous in the big boy sense, if and only if you are both left continuous and right continuous. So we are left continuous at B, but we're not right continuous at B. So we cannot possibly be continuous overall at B. All right, and then finally at x equals c, as I approach c from the right, my limit is equal to the function value. As I approach c from the left, my limit is not equal to the function value. So here I would say since lim x to c plus f of x is equal to f of c, the function f is right continuous. However, since the limit as x approaches c from the left of f of x is different than these, the function cannot be overall continuous at x equals c, and is also not left continuous at x equals c. I want to go back and clarify here just a little bit. So lim as x goes to b from the right is not equal to lim x goes to b from the left. But the limit as x goes to b from the left is equal to f of b. What I want to say there is that the left limit and right limit are different. The left limit is equal to f of b, but the right limit is not. So I apologize here. So that was a confusing bit of notation. And the thing that appears to be going on here is going on here. It's a theorem. I can write it in one line. Theorem. The function f is continuous at x equals a if and only if it is both left continuous and not one line, all right, and right continuous at x equals a. So to be continuous full stop means that you're left continuous and right continuous. Okay. There are a bunch of fun problems we can ask about continuity. I'll just grab one or two. No, that's a little boring as hell. Right, okay, so I should say this as well, right? A bunch of functions that you know are continuous everywhere in their domains. So polynomials, continuous everywhere. Rational functions, continuous everywhere on their domain, right? So as long as the bottom isn't 0. Root functions, continuous everywhere in their domain, right? As long as they're defined. Trig functions, inverse trig functions, logs, and exponentials, all continuous everywhere in their domain. These sort of problems are boring as hell. This one we will need. Let me go ahead and give you this. There's a way to say this in words that I like a lot more. Limits and continuous functions commute. Meaning I can pass a limit into and out of a continuous function. I.e., that is, if f is continuous at b and the limit as x goes to a of g of x is equal to b, then lim x to a of f of g of x is equal to f of the limit as x goes to a of g of x is equal to f of b. It's the first line that's really useful. The first equality that's really useful. So you can shove a limit into or pull a limit out of a continuous function. In fact, this can be taken as the definition of continuity if you want. It's very, very close to the definition. In the special case where g of x is the identity function x, this is the definition. Quick example here. This is a classic. Let's see, we haven't talked about those yet, have we? So let's do limit x to 0, inverse tangent of e to the x. Now, you know from your pre-calculus class that e to the x is continuous everywhere. And you may or may not know, but you should know that the inverse tangent function is also continuous everywhere. You can get it just by thinking about the graphs. Right, this is not cotangent. This is not 1 over tangent. This is arctan, or the inverse tangent function. In particular, since the inverse tangent function is continuous everywhere, I can shove the limit inside. So the limit as x approaches 0 of the inverse tangent of e to the x is going to be the inverse tangent of the limit as x goes to 0 of e to the x. So what I've used here is the continuity of the inverse tangent function to shove the limit inside. And then I can further use the continuity of e to the x. I know e to the x is continuous everywhere. In particular, it's continuous at 0. And that means I can take the limit as x goes to 0 of e to the x by just plugging 0 in for x. So this is the inverse tangent of e to the 0. What is e to the 0?
One.
Very good. What is the inverse tangent of 1? Let's see how I remember trigonometry.
Is it cosine over sine?
No, that would be cotangent, right? So the inverse tangent is a different animal. Let me, because I believe that probably 90% of people have that same thought in their head. Let me point you to something in the modules that I really want everybody to review. Within this trig review on Paul's online notes, there is a section on inverse trig functions. I want every single person who had that thought or think they might have that thought to take a look at this website. So the inverse tangent is arctangent is not the same as 1 over tangent, right? That's what they're saying here. It means something else. We say theta is the inverse tangent of x if x is the tangent of theta. So when I'm asking for the inverse tangent of 1, what I'm asking for is an angle theta such that the tangent of that angle is equal to 1. And there's an additional requirement. Theta has to come from negative pi over 2 to pi over 2, because that's the domain restriction that we use to make tangent a 1-to-1 function. Any guesses? An angle between negative pi over 2 and pi over 2 such that the tangent of that angle is equal to 1.
Is it 0?
Tangent of 0 is 0. So here's our unit circle. Down here at 0, we have the point 1, comma 0. So the tangent there would be 0 over 1, which is 0.
Is it 45 degrees?
That would be in degrees. Yep, that's correct. So at 30 degrees or pi over 6, we've got root 3 over 2, comma 1/2. So the tangent there is 1 over root 3. At 45 degrees or pi over 4, and we need to get comfortable working in radians. We will use radians exclusively in this class. At pi over 4, the tangent is root 2 over 2 divided by root 2 over 2, which is 1. So that's our guy. I'll go ahead and complete this portion of the unit circle here just for gits and shiggles. So this is the angle we're looking for, which is pi over 4. So the inverse tangent of 1 is pi over 4. I'm just curious really quick, and I'll end the class on this note. Give me a react, any sort of react, thumbs up react, whatever, if your trig class worked primarily in degrees rather than radians. Okay, so presumably the majority of us are quite comfortable with radians. I do have, if you're a little bit nervous about remembering the angles in radians or remembering the unit circle in general, I do have 2 special resources for that, which would be wise to look at while reviewing inverse trig functions. So if you want to worry about memorizing the points on the unit circle, This Patrick JMT video is great. This is how I did it myself. It's an old video. Here it is in the chat. And then the other one I'm looking for is slightly different. I think this is it. Is this it? Let me see.
Today we're going to do positive direction of the x-axis. 3/2.
Oh, this is not it.
4 pi over 6, which of course just simplifies to pi over 2. 2 pi over 6, which of course just simplifies to 2 pi over 3. 5 pi.
Although this
over
is not
2
bad.
here, which we can't
This is actually pretty good. But there is another one that other students have told me they like quite a bit. I think this is it. Yeah. All right, so check those things out if you're at all rusty on that stuff, because quick recall of these facts is going to be important as we go through the course. So this particular limit, the limit as x goes to 0 of the inverse tangent of e to the x, can be evaluated using continuity. We use continuity first of the inverse tangent function to shove the limit from outside the arctan to inside the arctan. And then from here, I use the continuity of e to the x to say the limit as x goes to 0 of e to the x is just what you get by plugging in 0 for x. Then from there, it's just like, do you know your unit circle? So these are things that we care about. These are things that you will need to be able to recall quickly on exams. So I do strongly recommend reviewing those web pages and videos if you find yourself struggling to recall that stuff quickly. That seems like a reasonable spot to leave off for today. Yeah, we can do any amount of this stuff. But that is really going to help you build skills. Intermediate value theorem, fun to talk about, but yeah. Let me just point at something and talk for a second. There's a problem in your homework that looks a lot like this. All right, you want to find the values of a and b that make f continuous everywhere. I want to point out that each of these pieces, rational function, polynomial, polynomial. Each of those pieces are guaranteed by our previous theorems to be continuous. The only place you need to worry are the places where you're trying to join up those piecewise functions. So for this guy, the place where you need to worry is 2, because that's one of the join points, and 3, because that's one of the join points. All right, there are problems like that in your homework set. And what you need to do there is use the definition of continuity. You need to see if the limit as x approaches 2 of f of x is equal to f of 2. That will give you an equation, right? Because you take the limit from the left, you'll be using this first part. Take the limit from the right, you'll be using the second part, and you'll set those two equal to each other. And you do the same thing at 3. From the left, you use this part. From the right, you use this part. You set those two equations equal to each other. And what you're going to end up with is a system of linear equations that you then need to solve. It's good practice reminding yourself how to do that stuff, because you'll need that later as well. All righty, gang, this is where I'm going to leave it for today. Please do work on that homework set from this week, the new homework, homework 2. If you need more time on the homework set from last week, homework 1, put in an extension request, even if you just want to play with the problems some more. It's no skin off my back. Please do it if you think you would benefit at all from looking at those problems some more. It's very important that you fully internalize the solution process, not just put the right answers into WebAssign. If you're feeling stuck on anything, office hours, Monday, Wednesday, Friday, 1 to 2 p.m., Tuesday, Thursday, 11 a.m. to 12 p.m., or you can Canvas message or email me for assistance outside between those times whenever. Take care, guys. I'll see you on Friday.